Can you say how you ended up choosing the coupling fields? Is that like trial and error, or is it a sort of a mixture of theory and practicalities and seeing what's stable?
It is a little bit trial and error. It's also, you can sort of anticipate which fields are going to work well with the averaging. So U and V, work on quite a large scale, whereas if you were to overwrite the vertical velocity, you know that that's very much on a sort of grid scale. And if you're averaging from one resolution to another, that's not going to do quite so well. So yeah, there's certain fields you anticipate are going to be on a larger scale and will work better.
Okay, thanks very much. Question from Colin, asking whether or not you could say something about the potential or not for a similar hybrid approach in the ocean. I imagine he's thinking about coupling the physical ocean to the biogeochemical.
Yeah, I mean, I deliberately, because it's an 8-minute talk, I deliberately didn't talk about the ocean. So there's some work that Clement Brical's done on coarsening, and that looks quite promising, but that at the moment works simultaneously. And so the issue with the ocean is that if we went to Walker 025, then we'd have to worry about the biogeochemistry being very expensive.
Right.
And so what Clement Brical's done is he's run the dynamical core ocean, the physical ocean at Walker 025, and he's run the biogeochemistry at Walker 075.
Okay.
And yeah, so that's run simultaneously, and we could look to do that, but I think we probably want to pull it apart in a similar way to what we've done with this hybrid resolution atmosphere.
Sure. Okay. One final question here, I think from Ranjini. She's asking, would this hybrid model approach carry through once we move to Elfric? So from a completely different, so moving off the UM to a completely different architecture for the grids.
Yeah, there's no reason why it shouldn't. I mean, a lot of the infrastructure we've built would need to be modified, but yes, there's no reason why it shouldn't. Okay.
Many thanks indeed, Mark. Very nice talk. Next up is Till, who's going to be talking to us today about time-dependent regional features of ocean heat uptake. Till, over to you.
There we go. Yeah, I just asked to be unmuted. Time-dependent regional features of ocean heat uptake in CMIP6 Earth system models. This is work I have mainly done with Aurore Valdois from CNRM, and also with relevant input from Met Office staff and Colin. A quick motivation, why are we looking at ocean heat uptake? Firstly, global ocean heat uptake traces Earth's energy imbalance very closely, and therefore is a very good and reliable metric of the current global heating. Second, regional ocean heat uptake reflects, if you look at it in the models, the simulated large-scale circulation patterns. And the good thing about ocean heat content is that we have a very good, relatively good observation since about 1960 for global and regional ocean heat content. So we can use these observations as a benchmark for analyzing the CMIP6 historical circulation. So in this study, we are using 5 observation-based data sets and compare these with 4 CMIP6 models. All of these CMIP6 models use the same ocean model. That's notable in NEMO Orca 1, the Chaco-NEMO configuration. So on this slide, you see that we've got in the central panel the UK models, that's UKESM in red, GC 3.1 in green, and on the right-hand side, the CNRM models, again, the Earth system model and the physical climate model. Let us focus, I should say, all the time series are referenced to the decade 2005 to 2014, and we're looking at simulated and observed ocean heat content anomaly referenced to this period. If we look at the bottom panels, that shows you the time period from 1955 to 2014. What we see for the UK models is that the global ocean warming rate since about 1975 is roughly realistic for the full depth ocean. The warming rate since 1991 is a little bit too high. So this is for the global full depth ocean. In the UK models 1965 to 75, there's no ocean heat uptake simulated, and that is in contrast to observations that clearly show 70 zetajoules ocean heat uptake in that time. Moving to the CNRM models on the right-hand side, we see that they are closer to observations, especially CNRM ESM2, the Earth system model. This is this amber line. However, their warming rate after 1991 is slightly too small. One of the core points really is that we kind of, this work strongly suggests that there is a strong link between the larger negative aerosol forcing in the UK models and the larger positive greenhouse gas forcing, or which translates into equilibrium climate sensitivity. And this has a direct influence on these ocean heat uptake curves. It's also notable for the UK that the behavior before and after 1991 is clearly different. Too little ocean heat uptake before 1991 and too much ocean heat uptake after that. If I go to the next slide, there we go. So this is the regional ocean heat uptake. So if we look at these top two panels here, then we see for the individual basins, ocean heat uptake in the simulations, in colors and observations in red, in observations in black and gray. This is now for the 0 to 700 meter ocean heat uptake, where the observation, the quality and density of observations is best. This is before 1991 and after 1991. These regions are simply the main three ocean basins, Atlantic, Indian, Pacific, cut in half along the equator. So we see that before 1991, the ocean heat uptake in the two CNRM models, blue and yellow, even in the individual basins, compares very well with observations, maybe a little bit too much here in the South Pacific, but otherwise and globally very close to observations. In the UK models, the ocean heat uptake is extremely small, way lower than observations. So there's a lot being missed out here. After 1991, for CNRM, they are still doing a very good job and capturing this ocean heat uptake here close to observations. But if we look at the red and green lines for the UK models, this is much too strong now. And interestingly, the overly strong ocean heat uptake is mainly occurring in the North Atlantic and to some extent in the South Atlantic, but not in the other basins. So the lack of ocean heat uptake before 1991 is the global phenomenon. The excess after 1991 just happens in the Atlantic. And thank you. And we can look at this on this slide here. We focus on the central panel here, which shows an ensemble spread analysis, so correlations among the ensembles of historical simulations. This is global ocean heat uptake. How does it correlate with regional ocean heat uptake and with the northward ocean heat transport? And what we find is that for the UK models, that's in red, significant correlations are hatched. There's a strong correlation with South Pacific ocean heat uptake throughout this considered period. But for the North Atlantic, there's only a strong correlation of the regional with global ocean heat uptake after 1991. It's different for the CNRM, where Southern Ocean heat uptake dominates throughout. If we look at the northward ocean heat transport, which is achieved by the meridional overturning circulation, then we see a clear difference here for the CNRM models. There's always a negative correlation. So this means stronger northward ocean heat transport goes along with less global ocean heat uptake. And this is exactly the opposite for the UK models, where after 1991, we have a strong ocean heat uptake in the North Atlantic basin. Which the CNRM models do not have. So both models, both types of models transport the heat northwards, but in the UK models, due to less ocean surface heat loss, there's an accumulation, and this does not happen in CNRM. And we believe that this is linked to the modes of centennial variability in these two classes of models, which are quite different. Southern Ocean focused in the UK models, but North Atlantic focused in the CNRM models. So last sentence is that although the ocean model is almost exactly the same across these four models, in the coupled setup and the emerging centennial modes, the behavior for ocean heat uptake is very different. Thank you.
Thanks a lot, Till. Very nice. Colin has a question. He says, do CNRM have any good ideas why their system model does a better job than the AO model for ocean heat uptake in the early period?
We don't have a very clear answer to that. I mean, it is noteworthy if I go back to this slide here, that the aerosol forcing is very different between the CNRM system model, which is just minus 0.82 watts per square meter in 2014, but we assume for the minute this translates in earlier periods, and CNRM6, where it is indeed much stronger. So that would be my test candidate.
Okay, I think time for one more question from Pat Hyder. He says, do you see expected aerosol-related spatial pattern signature in the UKESM heat uptake errors in the period of low warming?
I have not yet looked at, for this study, we have not looked at spatial patterns beyond these 6 ocean basins that I've been presenting today. But there is other work going on. I think there's there's other studies. I think Matt Mannery has led one where they have looked at the patterns of heat uptake. There's also the Robson et al. Access UKESM evaluation paper. They also have looked at these patterns, as far as I know. So these papers are available online.
Thanks, Till. Rowan asks, what do the observations say about the changing role of the Southern Ocean and North Atlantic contributions?
That's a very good question. It is generally expected from studies with observations and simulations of 21st century that historically North Atlantic heat uptake has been dominating, but going into the 21st century, we expect Southern Ocean heat uptake to be more dominant. And yeah.
Okay, thank you. Siobhan O'Farrell asks, are there differences in any of the model parameterizations that might have affected the ocean ventilation?
Yeah, we have looked into that. There are some parameterizations which have been used in the French model and not in the UK model, and vice versa. Some parameters have slightly different values, but from what we know on how these parameterizations, the impact of these parameterizations would not be that much large scale or affect global large scale patterns as what we see here.
Thanks, Till. Andrew Yule asks, ocean carbon uptake has a strange east-west pattern in the North Atlantic, more on the east, less on the west, presumably reflecting circulation. Is there anything similar in heat uptake?
Very good question. I mean, what I know is that the ocean heat uptake, if you look at the spatial patterns and deep water formation, Our 1 degree, or UK 1 degree ocean prefers to do that in the northeast Atlantic. And that might lead to these patterns. And as an aside, this pattern looks different in the Orca O2-5 ocean. So it would be interesting to look at these patterns in the 2 spatial resolution versions of HM3 GC 3.1.
Many thanks, Phil. Good talk, great answers. There's some more questions for you in the chat. Pick those up in the Google Doc, please. We're going to move on to James Keeble from NCAS, who's talking about evaluating stratospheric ocean and water vapor changes in CMIP6 models. James.
Yes, thank you. I'm unmuted and I have control of the slides. Perfect. Yeah, so I'm going to talk today about some work a large team contributed to, and I was involved in late last year, evaluating stratospheric ozone and water vapor changes in CMIP6 models. And I'll give a brief overview of that work, but more details can be found in the ACPD paper. The link is here on this title page. So stratospheric ozone and water vapor, why are we interested? We're interested in these because both of these are really important climate kind of gases impacting surface radiative forcing and climate. And for stratospheric ozone, this is particularly important regionally. So we think of the classic Antarctic ozone hole kind of really strongly drives recent decadal climate changes in that region. And so getting the long-term baseline stratospheric ozone correct and then the recent changes is important for regional climate. Okay. So I'm showing here on the left kind of time series from 1850 to 2100 of total column ozone averaged for different regions. So this is the kind of near global average in the top left, and then as you move through you go from the southern hemisphere to the northern hemisphere. And this is the CMIP6 multi-model mean, black for the historical simulation, and then in the different colors the different SSP scenarios. And you can see in the parentheses here the number of models which contribute to this multi-model mean. And so we see kind of from pre-industrial times, total column ozone has remained relatively constant or slightly increased with increasing CO2 concentrations in the atmosphere for around 100 years. And then with the onset of anthropogenic chlorinated ozone depleting substances, strong decreases throughout the kind of 1960s, 70s and 80s, reaching a minimum in 2000, and then projected recovery back to the 1960 values over the course of the 21st century. And the timing of this recovery is dictated not only by the kind of removal of chlorinated ODSs from the stratosphere, but also the emissions of other greenhouse gases. And so in general, we see that total column ozone values return sooner to their 1960 or 1980s TCO values shown by these horizontal lines. They return faster with more kind of with higher CO2 emission scenarios. And the region where that's not true is in the tropics, where we have an interest in chemistry climate feedback, where the ozone changes expected through ODS changes are offset to some extent by a faster Brewer-Dobson circulation. Okay, so that's the column, but then we can see in the zonal mean that the column actually kind of combines a large number of changes occurring at different altitudes. All of the future SSP scenarios assume that chlorinated ozone depleting substances will decline following compliance with the Montreal Protocol. But of course, all other greenhouse gases and radical source gases evolve differently. And so we can see here in the zonal mean on the left, the SSP 126 scenario, and on the right, the 585 scenario, very different changes in tropospheric ozone based on the emissions of ozone precursors, in the middle stratosphere based on effectively the speed of the Brewer-Dobson circulation, and then in the upper stratosphere based on both the ODS loading and the CO2 loading. So really these total column ozone changes are driven by quite distinct regional changes in altitude. And of course, another thing that the CMIP6 multi-model mean hides is really the spread in the individual models themselves. So here on the left, we have exactly the same plot as before, but only for the historical period, and now showing all the individual models which contributed to that multi-model mean. The multi-model mean here is still in black. And we can see really quite a substantial range in total column ozone values, both at the present day and extending back into the kind of pre-industrial period. And then for UKESM-1 relevant work, UKESM-1 really is kind of the outlier for this range, with very high total column ozone values throughout the length of the run. As I say, really there is a staggering range in total column ozone values here, especially given, to some extent, the kind of simplicity of stratospheric ozone and the negative feedbacks that you would expect. So exploring how and why this range of values exists is really something that we want to get to grips with over the rest of this year. But we can see that this difference in total column ozone is coming from, again, in the zonal mean panels here. This is the zonal mean ozone for these individual models, their difference to the multi-model mean for the present day period, 2000.
James, are you there?
I think we've lost James.
Yeah, I was wondering whether it was me it disconnected, but no, it looks like he has.
Yeah, I can't see him on the list. Shall we perhaps come back at the end, and then if there's any questions for James, cover it then?
Yeah, no, that's fine. That's fine.
We may have enough time for him to complete his talk at the end, potentially.
Yeah. No, I think that's okay. We're doing pretty well for time. Okay, well, I'm going to thank him in his absence and look forward to hearing from him again. Next up, we have Leighton Regayre, who's going to be talking about perturbed parameter ensemble of UKESM-A to understand aerosol forcing. Leighton.
Hi, everyone. Thanks very much. Ken Castle has invited me to present our ACURE perturbed parameter ensemble. It's an ACURE NERC-funded project, but it's using the UKESM to understand aerosol forcing. Obviously, making these perturbed parameter ensembles requires a lot of expertise from a lot of different people. This is our core team here and people who've contributed meaningfully. I've forgotten to include Anja Schmidt, who's a co-I on our project. So instead of being on the list there, she gets a special mention. Thank you, everyone, for your contributions. So before I dive into telling you about the UKESM PPE, I want to give you some insight into the analysis of PPEs over the last couple of years that have really informed the design of this current perturbed parameter ensemble. So we've got a couple of perturbed parameter ensembles of GA4 using parameters like 26 aerosol parameters that we perturbed simultaneously, and we contrasted that with a PPE where we perturbed 27 aerosol and physical atmosphere parameters at the same time. And that made it really clear that we need to include physical atmosphere parameters if we want to get a comprehensive assessment of uncertainty in aerosol forcing. They contribute about 50-50. We've also got a methodology of constraining the aerosol forcing where we emulate using statistical emulators, model output from the ensemble, and then we take really large samples. In our case, that means 1 million model variants that represents different parameter combinations. And we challenge those model variants using as diverse a set of measurements as possible. In this case, over 9,000 measurements allows us to constrain the aerosol forcing by around 20%, which is a meaningful constraint. We've ruled out the strongest forcings, but it's not anywhere near as tight a constraint as we were expecting with such a large set of measurements. So we've reflected on that in the designing of our UKESM perturbed parameter ensemble. And some of the things we know that are limiting our ability to constrain the model output is that we've compared output from a single year of output from simulations that are nudged to era interim meteorology with data that's been collected over many, many years. And therefore, we've had to include an interannual variability term in our model measurement comparison, which has meant that we've rejected far fewer model variants than we'd like to. And similarly, we've compared only monthly mean data, which is the resolution we kept for our previous PPEs, with measurements that are taken at a much finer time resolution, and that's limited our constraint. So the other reasons we've had limited constraints is, if you look on the bottom left here, these are constraints of some anthropogenic emission parameters. The one on the left, top left in blue, is anthropogenic SO2, and it's reasonably well constrained. If these were unconstrained, they'd be fully colored in from uniform probability distribution functions. This one's reasonably well constrained, which implies that lower values of anthropogenic SO2, model variants with lower values, are consistent with the measurements. But some of our other parameters, like biomass burning emissions in diameter and fossil fuel emissions in diameter, they're not well constrained at all. And the reason for that is that if we constrain in one region, we constrain, and model variants with higher values are consistent with the measurements. But in another region, model variants with lower values of these parameters are consistent with the measurements. So in other words, we're getting conflicting regional constraints. That means we're getting no overall constraint of these individual parameters. So we know that we have to perturb our anthropogenic emissions on the regional basis rather than globally. And we're also, with our constraint efforts, challenged by the problems with model equifinality. So it doesn't really matter about what two parameters these are. You can see them there. But this is the density of our constrained sample. And you can see that there's many, many different ways of configuring even just these two model parameters to get equally plausible model variants, which implies that we need to take a lot of diverse measurements to constrain our sample, which means we run the risk of ruling out all of our model variants if the measurements are too diverse. Therefore, we need a really large sample, and that means we have to take a more inventive approach to creating our perturbed parameter ensemble that gives us a sample that's really close to measurements in the first place, rather than being as diverse as possible. So here's the main features of our UKESM PPE. And we call it a UKESM PPE, but actually it's got a -A on there because we're only perturbing the atmospheric component. That said, it is a UKESM PPE because we've taken a fully coupled version of the model and taken output from that to use as boundary conditions for the atmospheric component. So what does that mean? That means we took DMS seawater concentrations from the coupled model. We took BVOC SOA concentrations. We took oxidant fields to read in as boundary conditions. And we perturbed all of those because they're also uncertain. So we perturbed 55 aerosol and physical atmosphere parameters. That's more than double what we've done previously. And it brings us on par to what David Sexton's done with his GA7 PPE. So it's a large number of parameters to be perturbing with only a couple of hundred simulations. But that includes regional anthropogenic emission parameters. Not only that, but we've done a two-stage creation of our perturbed parameter ensemble. So we ruled out lots of model variants that were inconsistent with global mean values, global mean measurements of top of atmosphere fluxes and precipitation and cloud drop concentrations, for example. And that means that the subsample of model variants from there that we use to create a new perturbed parameter ensemble are going to be much closer to global mean values at least. We've used a meteorological year to nudge our simulations that includes lots of different flight campaigns. So we'll have loads of in situ data and satellite information from a single year to be able to constrain our PPE, which means we've ruled out the effect of internal variability. And we've got lots of high time frequency output. So stuff that's measurements that are on the daily mean, as well as some 3-hourly data on the flight tracks that I mentioned. I should point out that it's a community resource and we welcome anyone's use of the PPE. If you find something interesting about it and want to know how the UKESM is working, then please by all means get in touch. And in the last couple of minutes, just a few early examples of what the PPE looks like. We haven't done any sophisticated statistical analysis here. This is just a first look at the 221 ensemble members. And very briefly, just to show that there's some clear controls over some model output. This is an updraft parameter, updraft velocity parameter, and it's control over cloud drop number concentrations for June. And this is global mean values. And this is a really strong control over that parameter because the only noise in this relationship is coming from the other 54 parameters that are perturbed simultaneously. So it's clear to us that we're going to get a constraint over one of these main controls that's going to affect the aerosol cloud interactions from cloud drop number concentration retrievals from satellite. And similarly with sea spray and AOD. And at the very bottom here, this is again just the first impression of the linear fits in every model grid box between parameters at the bottom and the variables at the top. And these are the gradients that show the relationship there. So we've got a clear indication that our regional scalings are having a regional effect that aren't usually dispersed beyond that. We know that we have to look beyond global mean values because some of our parameter perturbations are going to have contrasting regional effects that will compensate in a global mean value and be hidden. And finally, we know that some of the new developments in the UKESM, such as the primary marine organic emissions that we've perturbed here as a scale factor, they're going to be really important for our aerosol radiative forcing. This is its effect on ice water path in June, and it's quite substantial. I'll stop there. Thanks very much.
Thanks very much, Leighton. Very nice. Nobody is asking anything yet, so let me confess my ignorance and ask you to say more about the problem of equifinality, the way in which you are filtering out undesired combinations of parameters. I've got the idea that two sets of parameters can have different values and produce the same result. Is that what you were trying to say there?
Yeah, that's exactly right. So it'll be, not go too far. So there's lots and lots of ways if you could come up with a single tuned model version to release, and as was used in CMIP6, you have to have a well-configured model version that represents historical and present day data. And so you can here increase just two parameters, your sea spray emission flux as a scale parameter, but also at the same time increase the removal rate, your dry deposition in the accumulation mode. And that gives you equally plausible model variance. And that's only in 2 dimensions. Of course, that's much more complex when you have multiple emission sources and multiple removal processes. So how we're working with that and how we're approaching that is to have a really large sample, is what I was implying. So rather than 1 million model variants, we're going up to 4 million. And that's to avoid ruling out all of our model variants, because it'd be really easy with a lot of different measurement types to end up with no model variants at all that are equally plausible for all those different metrics.
Sure. Okay. Thank you very much. Question from Colin. How are you going to deal with systematic biases in some of the UKESM-based boundary fields, such as PMOA, DMS, vegetation, and so on?
Yeah, that's really important. So that's where our interaction with everyone else in the UKESM community is really important, so that we know about those biases and where they are before we begin our analysis. But we have a process that allows us to identify where the ensemble distribution doesn't match with the measurements at all, and that's a way of indicating where the structural biases in the model are. So that's usually what we do in the first part of our analysis. What we're considering doing is to identify where the structural biases are most important. But the other thing we're going to do is make sure we don't rely overly on a single set of measurements for the constraint. We have a constraint process that makes sure the model variants we retain are plausible over multiple different metrics. So that minimizes the effects that those biases would have.
Okay, thank you. A question from Jane. PMOA doesn't influence the LWP directly. Do you have a feeling for how this impact you're seeing is coming about?
I think, Jane, we have to look into that together. It's probably going to be through the liquid water path, aerosol concentrations in that region, and the cloud fraction in that region, but it requires more steps in that analysis. You're absolutely right.
Okay. Graham Mann is asking, did the key parameters identified from the ECUR PPEs also play as influential a role within the GA40 PPEs, or was the model more sensitive to some at version 11.2?
So I'm sure if David Sexton's still here, he'd also point out that this work of creating a perturbed parameter ensemble is always work on shifting ground. The model version continues to move. So yes, deposition fluxes and sea spray are controlling aerosol concentrations to a large extent, but we've changed a lot of the model structure. So we have, like I say, primary marine organic emissions that change the relationships in the Southern Ocean. We have a different configuration of the updraft velocity here, where it now depends on the turbokinetic energy rather than being a globally applied scaling. It's applied to those values in a different way. So yes, the same parameters are largely contributing, but there are subtle differences.
Okay. Last question from David Stevenson. You mentioned several parameters didn't constrain the system much, but which parameters did? Are these robust? And is the plan to focus future work on these?
So just briefly, we've narrowed the range of some of our perturbed parameters based on the constraints that we've already achieved. And so we anticipate that they'll still control a lot of the uncertainty, like the dry deposition fluxes we haven't been able to constrain. But yes, there's other parameters that will now be taking a larger or contributing more to the variance than they did previously. And we'll let the analysis guide where we're taken rather than focusing on what we knew from previous from here on. Thanks very much.
Okay, thank you, Leighton. Thanks very much indeed. The last talk for this session is from Rob Parker, who's going to be talking about work called Climate and Earth System Change at Different Levels of Global Mean Warming. Rob, over to you.
Yep, I think you just unmuted me. Can you hear me okay?
That's great.
Cool, okay. Yep, so I'm going to talk about some of the work we've been doing in the UKESM core group on looking at climate change at different levels of global warming. And this really is just the first early teaser of what we think will be the baseline for a lot of other activities and work to jump off through for over the next year or two. So this is work that Colin's leading and Jeannie's done a lot of the initial analysis for, but there's a big group of us in the UKESM core team who are involved with this. Okay, so what are we actually going to do? So as well as normally looking at the evolution of the climate over time, we can flip that around a little bit and look at what the state of the climate looks like when we get to a certain state. So rather than look at the temporal evolution, we say when the climate has got to 2 degrees, 3 degrees of warming, what does the state of the system actually look like then? So the sort of questions we can ask are, how will the climate and Earth system look at different levels of global warming? And more importantly, what regional changes and therefore associated impacts might be avoided if global warming is limited to X degrees instead of Y degrees? And we can also then analyse changes in the coupled Earth system at these different levels of global warming. So using the UKESM-1 and the scenario MIP multi-model ensemble. And this schematic on the right kind of shows what the concept is behind this. So we have the blue line, which is our climate temperature record. So this is one example from a scenario MIP data for UKESM. And what we do is we smooth that with a 21-year running mean, and we run that smoothing until we get to an average global temperature above the 1850 to 1900 average of whatever global warming threshold temperature we're going to look at. So in the example you can see here, I think you can probably see my cursor, we run this for the 3 degrees global warming threshold. So when the world has warmed by an average of 3 degrees from the 1850 to 1900 average, we can then look across, and first of all we can work out what year that happens. So for this example, in this particular scenario for UKESM, with this particular rolling window, we exceed the 3 degree global warming threshold in 2058, I think that is. So therefore we have an exceedance year. So we're going to talk a lot in this presentation about different exceedance years, and 2058 for this particular temperature record is the exceedance year for this scenario. And if I go on to the next slide, what we can do then is look at these different exceedance years for lots of different scenarios from UKESM, and we can also look at the giant multi-model ensemble for all the different models. So I'm going to spend a little bit of time just describing this plot now. So I'm assuming everyone is familiar with the different SSPs, but if not, this schematic here kind of gives you an indication of what we're talking about. And on this figure, what we've done is we've taken the different global warming thresholds that we're concerned about. So we've got the 1.5 degree, 2 degree, 3, 4, and 5 degree. And then we've plotted the spread of the exceedance years. So these are defined, as I just explained in the last slide. So this is the year at which the global average first gets to that temperature. And what we plot here is the individual model points. So we're looking at the CMIP6 ensemble here. So each individual circle is a CMIP6 model, with the CMIP6 model, multi-model mean as the cross, and UKESM is the square within this distribution, with the UKESM spread being the bar across the UKESM mean. And we do this for the different SSPs. So you've got the purple, blue, yellow, and red indicating the different SSPs. So if we start at the 1.5 degree, so this is when has the world got to 1.5 degrees above historical. What we see straight away is that one CMIP6 model is already there in 2010. So even before they do their projections, they get to that increase in their historical. UKESM, if you want to try and find us in here, is here. So we're quite warm. We're kind of in the middle of here. So in the next couple of years, UKESM would be expected to get to the 1.5 degree level for all the scenarios. It doesn't really make a difference which scenario we're looking at here. If we look at the 2 degree threshold, a bit again now in 2020, one of the models is indicating that we should already be there based on their projections. And UKESM again is shown as one of the warmer models, but we know that because we have a warm climate sensitivity. But you see there's quite a large spread in models, and interestingly, this number here indicates that some of the CMIP6 models don't reach that threshold within the 100 years up to 2100 that we have. So in this case, using the SSP 126 scenario, 6 of the models don't exceed the 6 of the models don't or do? Yeah, 6 of the models don't exceed that temperature threshold. And if you go up, for example, if you go to the really extreme scenario cases, for example, SSP 585 at 5 degrees, only a handful of models do exceed that temperature. Most models don't get to 5 degrees by the end of 2100, but a few models do. A few models get there as early as 2060, are already getting to 5 degree average. And this is all talked about exceedance years in terms of the global averages. But what we can also do is look at regional differences. So we've got lots of different parameters to look at, and we've got lots of different combinations of these kind of plots. And Ranjini is going to present a lot more of this next week at the NCO annual conference, but I'm just going to show one example based on spatial seasonal patterns of surface warming. So here we're doing comparisons between what global surface temperature looks like for December, January, February, and June, July, August at 2 degrees and at 4 degrees global warming thresholds. And we've highlighted some key features in the different boxes around the edge of what we see. Now, first of all, interestingly, you see the summer warming, so June, July, August warming at 2 degrees is amplified by about 75% in Central Europe and Mediterranean and Central North America, Mediterranean, Central Europe. When we get to at both cases, but especially at 4 degrees, the Indian subcontinent warms less than the global mean during the summer monsoon. So that's kind of to be expected, but that's an interesting feature to note here. You're getting, over the Indian subcontinent, you're getting much less warming because of the monsoon.
2 minutes.
At 4 degrees warming, we see high latitude winter warming can exceed 8 degrees, and this tops out our colour scale. It can actually go even further than 8 degrees. So we get very high Arctic amplification of warming at the 4 degree level in the winter. And here you see 50% or more amplification of mean warming over the Amazon at 4 degrees. So we're not seeing necessarily linear effects as we go from 2 degrees to 4 degrees, and we're not seeing those happen globally. They are happening very regionally in certain areas. So really the idea is then that we break this down a lot more. We do a lot more future analysis. And the idea is basically these initial exceedance years that Ranjini has calculated are now starting points for us to do a lot more work on looking at impacts and the behavior of the model. And these are just some of the many, many ideas that we've got of things that we can really build on this for. A few things we need to do first is some of those changes I just showed you. We do need to look at how those changes compare to the internal natural variability within the models. So we don't want to be drawing conclusions from things changing when they may well have changed by that amount in the PI control or in historical already. And we want to then look at the sensitivity of these changes per the global warming threshold to different SSP pathways. So by that we basically want to look at, does it matter on the trajectory that a model has taken to get to a particular state, or is the trajectory less important than the characteristics of the state when we get there? And there's lots of things to explore in that. We plan to extend this out to other variables, so precipitation, evaporation, soil moisture, etc. And we already have lots of plots and analyses of those. I think Ranjini is going to show some of those next week. We want to extend this to higher time frequencies where we can better address some of these kind of impact cases. So things like heat waves, droughts, extreme rainfall, windstorms, etc. and then extend these to impact relevant metrics, so drought duration, water availability, so things where we can start talking in the same kind of language that policymakers talk about. Can we start being able to use some of these impact things? So start doing some kind of impact where we can then start advising, interacting with the impact community and then advising towards policy. And obviously we have sensitive regions. We've already shown from the last plot, the regions don't all perform linearly in the same way. We get some regions are key region hotspots, and we need to understand the behaviours and the processes in those. And we also want to look at the covariability of these changes impacts across the whole Earth system. So not only do we want to look at the physical parameters like precipitation, temperature, we want to look at things like vegetation, carbon uptake, air quality, etc. All of those are things that we can do in UKESM-1. And then even beyond that, we want to expand this out to marine changes and associated impacts. And all of this is within UKESM, but with the framework that we've built now, we can expand this out quite easily, as I showed in the first slide, to the whole CMIP6 multi-model ensemble. So like I said at the start, we're planning this to be basically the baseline of which we can now jump off a lot of work, looking at different impacts, different types of behaviour at different global warming thresholds. And that's my last slide, thank you.
Many thanks, Rob. Quite a few questions here. Let me start with Peter Cox, who says this is a good way to make your result less dependent on ECS-TCR. How sensitive are your conclusions to the scenario, though?
Yeah, so one of the things we're going to do is look at, I think I've tried to explain it very well, but maybe Colin or Regina can explain it better, how important the trajectory of how we get to a certain state, so i.e. which scenario we've gone through, how important does that matter versus what temperature we actually get to when we get to the state. So what the Earth system is at that temperature versus the way it's got there. And we need to try and decouple those a bit by looking at different scenarios. So that's why we've got a list of 4 or 5 scenarios already. We might extend this to more scenarios or look through the wider CMIP6 ensemble. But yeah, basically we want to disentangle that trajectory from the state and work out exactly as you say, how sensitive are we to the particular scenario that we're looking through.
Okay, so a variation on that from Doug. Is there any scope in overshoot scenarios, how different the system looks when it hits a threshold from the other direction?
Yep, exactly. So
only go to 2100, but some of these scenarios have been extended past 2100, haven't they?
Yep, and exactly. Some of the scenarios for some of the parameters, for example, for methane, for example, goes up and then comes back down. What effect would that have once we have a fully coupled system like Gerd was presenting earlier? How would that change versus some of the other trajectories and in the driving data? So I think, like I say, this is just the very start, and there's a lot of things, even just brainstorming it between ourselves, there are lots of other things, as you can see on the screen, of things we'd want to look at. And I think the more we talk to people about this, the more other ideas that people have that would be interesting to look at. And I think certainly looking at things like the overshoot scenarios would be one of them.
Thank you. Julian asks, are the regional temperature changes similar for the same global temperature changes on the different scenarios?
Let me just digest that question. So, no. So I think what you mean there is that are some of these changes linear depend? So when we go from 2 to 4 degrees, do we see a similar regional change from 2 to 4 degrees? And I think we've only done initial analysis looking at some of these things, and we still need to really break it down regionally. But I think we are seeing non-linear responses in some of these areas, and at the minute, this is very much a show and tell, this is what the model looks like, but really the point of this is getting to the processors and being able to explain why are we seeing those kind of non-linear responses over the Arctic, over the Amazon, etc. And I mean, even just from the initial plots, I think we see this dramatic increase in Arctic amplification that I showed. We see this temperature response over the Amazon doesn't seem to be linear when you go from 2 to 4 degrees. So I think there's lots to look at there, but I think the early indications are they're not necessarily linear, and we have a lot more to dig into to work out why.
Okay, many thanks for that, Rob. Nice talk. What I'd like to do now, please, is bring James back in to finish off his talk, and let us give him the benefit of our questions that we had. So welcome back, James. Nice to have you again. Sorry about the dropout. It's a miracle this stuff works at all, let alone that anything goes wrong. So over to you. Thank you very much.
Thank you. Yeah, there was a single peal of thunder, and now the Wi-Fi router looks like HAL 9000. But we're back. Okay, so a very brief kind of recap. So I was just saying that there's quite a large variation in zonal mean and total column ozone values across the CMIP6 models. And the same is true for stratospheric water vapor. So stratospheric water vapor is controlled effectively by how much water vapor is entering through the bottom of the stratosphere, through the cold point, and then also methane oxidation. And the CMIP6 models are very different. So again, we can see here the time series of 70 hectopascal water vapor. So this is kind of a measure for how much water vapor is entering the lower stratosphere. Again, black is the ensemble mean, and then the colors are the SSPs, and now the dashed line are the observations. And so in general, the multi-model mean is dry compared to the observations, but we see a progressive increase in the amount of water vapor throughout the 21st century. Kind of the higher the rate of forcing of the scenario we're interested in, the larger the water vapor increase we see. But then we see here in these lower panels kind of the same plots, but for the individual models, and we can see that some are very moist, some are very dry, and there's a true range in kind of not only the entry values, but I plot here the kind of oxidation of methane to give water vapor, and this should give a theoretical slope of 2 water vapor molecules per methane molecule. And some of the models, some of the Earth system models are capturing this slope very well. Others not so well, and others clearly don't have any water vapor production from methane at all. So as with ozone, we see that stratospheric water vapor is very different between models, and we understand why that is. But what we need to think is, you know, how do we improve this moving forwards? And then I'll stop there and take any questions.
Well, thanks, James. Good to have you back. Colin has what he calls an obvious question. Why is UKESM-1 an outlier? And is it wrong compared to the available observations for stratospheric ozone? Yeah,
so that's actually something that myself and a fairly large team of people have been working on now, and we think we have a pretty good handle on that. So we've built up a new version of UKESM-1, in which we update particularly the photolysis rates, but all the kind of chemical rates, the heterogeneous chemistry, and then some of the ways we treat hydrogen in the model, and we've already reduced that bias by about 30 Dobson units. So now we're well in the pack, but it seems to come predominantly from outdated rates information that was being used.
Okay. That's fine, James. Thank you very much indeed. Do appreciate you coming back to conclude your presentation and to take those questions. I'm going to bring our session to an end here. I'd like to thank all of our speakers this afternoon for some excellent talks, and also our questioners and answerers. Do remember, speakers, that all the questions have been transferred into the Google Doc for this afternoon. And you can continue the discussion with your interrogators there. We're going to take a break now, and we are coming back at 3 o'clock, as I said, for an open discussion, summary and outline of discussions for the 1-year extension of the UKESM-1 project. I'll leave that there. Thank you very much.
So what I thought we'd do, we've got about 45 minutes, and I have to say I'm not a big fan of final discussions at the best of times, possibly even less so when they're done by Zoom, but we'll see how it goes. So there's 3 items that I thought we'd spend a short while, at least trying to exchange some information. I've just got a few slides to try and prompt things. So one is a reminder that we have only about 10 months formally of this project to continue. So it formally ends at the end of March 2021. But as we've said, we have got this 1-year extension that we've been asked to propose, and I think we largely expect to get the extension. I don't want to tempt fate, but I imagine we have to do a very poor job not to get the extension, but that might be me tempting fate. So to some extent, we might have 22 months running. And then we do have this potential second LTSM, but I stress that is very much potential still, because those topics are still at the stage of discussion. So what I thought is we could just have 3 items, and briefly I'll try and invite people to comment. I've asked a number of other people to keep an eye on the chat as well. So what I'd suggest, and I cannot do that on my own, is if you've got a comment that you would like to raise, if you use the raise hand in the chat facility, so you click on the raise hand button, then if I don't see it, which I'm likely not to, one of my co-conspirators, and I asked a few people to keep an eye on it, will step in and tell me there's someone that wants to say something. Equally, if you don't get covered, I apologize for that, and please put any comments into the Google Doc, the final session Google Doc, because everyone's input is appreciated. So I'm just going to spend 2 minutes on each of these and then just see where we go with discussion. And if it proves that it's too awkward to discussion, then we will cut short and everyone will have an extended afternoon instead, in the hopefully in the sun. In Exeter, I think it will be in the sun in about half an hour. All right, and I'm not going to help you stay down because we've got things. So first on the final 10 months and then the 1-year extension. So one of the questions, given what you've heard and what a lot of you know about what's going on beyond what you've heard, are there any key aspects that we should be focusing on? First in the upcoming 10 months, but probably also feeding into the 1-year extension. And I'm going to have the next 2 slides just tell you at least where we've got to in discussions of that 1-year extension and what we might propose to include. And I think for a number of you, of course, what we propose doesn't necessarily impact on what you do anyway, but it might have some bearing on a number of people. So some of the things I think, at least in the core group, that we kind of know that we will be doing over the next 10 months, we will be continuing to make sure the data from the CMIP6 simulations gets onto the Earth system grid. In my view, that's an extremely important thing. There's no point us making these simulations if we don't make them available to the entire international community so that they can be part of the full CMIP6 analysis. So I've stressed the importance of that many times to the people that are shackled with having to do this, but it's really important, and that goes even for the MIPS where they're a little bit more distributed and being done by not necessarily people in the core group or at the Met Office. We will try to engage with you and make sure the data gets onto the ESGF. Again, in the core group and more widely, we've got a few what I've called evaluation/analysis papers that are still ongoing, and I think it is important that we get those done and completed, because they form a useful reference for that subsequent analysis of CMIP6 simulations. If there's something to lean on in terms of this is what the model consists of and this is what it does in some kind of X setting against observations. That doesn't preclude numerous other papers, but I think it's important we get those documentation papers done. We are trying in the group now to emphasize a little bit more looking at the future projections and less at the sort of model state. And we're not trying to stop do evaluation of the historical and all the other ones, but we really feel we need to be looking at what to some extent the model is developed for, and that's to say something about the future. So we are trying to move in that direction, and the last talk you heard from Rob is one area where we're beginning to move things there. It's not the only one, but it's one where we're beginning to move into that space. And one thing we are acutely aware of is that the UKESM-1 has a number of shortcomings, and 2 of them I've listed there, and they revolve to some extent around the representation of the historical surface temperature record. That might just be, of course, a reflection of the problems elsewhere. So we know our model has this mid-century cold bias, and we think we have some lead-ins as to why that is. I think we also know our model does warm too rapidly, sort of post-1991. And I certainly think that this is linked to, and Isabel, that model has a high TCR and ECS. I haven't written too high there. I've just written high. And I think those are things we definitely need to understand, even if we don't specifically improve them in this model, which would be nice if we did, but we need to understand them for future model versions. So I have a question now about whether there's any other pressing problems. I think one was raised already about stratospheric ozone. And then the other topic that we are emphasizing in the core group is we do want to get this computationally fast version and the hybrid versions working scientifically acceptable, and probably with a first documentation of the 2 of them as well. I'm going to say what's coming in the 1-year extension for 5 minutes, and then I'm going to stop and see if there's any comments and contributions. So for this 1-year extension, for those of you that are not aware of it, NERC gave out a call essentially asking all these LTSM projects to make a 1-year proposal extension. So I've had 2 meetings already with some of the representatives from the NERC centres, and they're online now. And we've got a 3rd one tomorrow morning to follow up from this meeting, where I think we'll hopefully be close to agreeing at least the main themes, but this chat now may change some of that. So we're supposed to build on and extend what we've done in the 5 years. Now there's some caveats to that, of course. What we propose needs to fit with the respective centre interests, and also with the involved staff, because it's very likely it'll be the same staff going into this 1-year extension. So we need to fit the skill set. And it's NERC are saying that we really should not be, at least visibly, proposing things that assumes a second LTSM afterwards, i.e. the bulk of what we do should be realizable in that 1-year extension. Now for Earth system modeling, clearly this is not an easy thing to cover. And I definitely do not intend us to cut our ties with the community we've built up that are working on UKESM-1, be it analysis or model development. And we will carry on doing some model development. We just may not make it explicit in the proposal. But the 1-year extension should ostensibly be around scientific exploitation of what we've got, not further development of something for the future. So we've proposed 3 themes. I'm going to put a little bit of meat into that and then stop. And the 3 themes are investigating and quantifying future Earth system change, understanding the historical past to constrain the future. And the 3rd is to support and keep interaction with the user community and the model developing community outside of this project. So just one slide on each, and then I'll stop. So on investigating and quantifying future Earth system change, we're thinking about things like understanding and constraining the feedbacks our model is representing, and to the extent we can to constrain those and also to put them in the context of other models. So UKESM-1, we really bend over backwards to make it what I call prognostically coupled as much as possible. So that means we really do have coupling that can change into the future. So that's interesting, but it's also a risk, of course, because it means our historical model has more, our historical simulations have more degrees of freedom, so have more potential to go wrong. But we have more chance of looking at interesting feedbacks in the future. So we want to emphasize that, both understanding what they're doing and where we can constrain them. And I've listed just some examples there. Then we also want to have a topic which is a little bit along what Rob outlined, but it doesn't only have to be in that context. And that is to look at simulated Earth system change and the implied impacts, both on society and natural ecosystems, at different levels of global warming. It doesn't only have to be at different levels of global warming, but that's where we've decided to put some start in the core group anyway. And to do this in the context of both physical and Earth system changes, with one emphasis maybe on land, and that Rob reflected that way we were concentrating on land, changes over land, and trying to link to impacts research later, but also over the ocean and in the ocean and in the same guise. And then we've got a 3rd emphasis where we explicitly want to make more use of the Greenland-Antarctic ice sheet model. And as Robin intimated, because I've kept pushing him on that, to say something about the impacts of having that facility on both sea level risk and ocean circulation. And then the other 2 themes is, one, to try and understand a bit more the historical past and where we may be going wrong in our own historical past simulations, and try and constrain them better with multivariate constraints where we can, like radiative forcing, energy imbalance, and where the energy goes, and the Earth system responds to that as well, potentially with the aim to make some targeted improvements to UKESM-1 or 1.1. As some of you will know, we hoped 1.1 would be a significant improvement, and it's proving only to be a modest improvement, but it is an improvement at least. So we want to keep going in that direction. And then the 3rd one is we definitely want and have to keep interaction with the wider community. And that means things like making sure our model releases are up to date in the respect of unified model releases, ensuring that we have interact with people that are developing parameterizations that they want to see coming through into the full Earth system model, and also supporting the use of tools such as the ESM-Val tool. And one thing we've talked a bit about is maybe trying to use the fast version of the Earth system model to make a large ensemble that we may not make directly available through the CMIP system, but we try and make available to the UK community somehow. And for the 1-year extension, we also talked about having a couple of workshops where we try and broaden our user-based interaction outside of what we classically the physical and earth system modeling community, to have a workshop where we talk more with climate policy people about their needs and their requirements for system modeling, and then one more with the impacts and research community. So with that, I'm going to stop and just see whether there are any people that have comments specifically, and I am going to be relying on other people to tell me. So I can see Dave Stevenson and I thought I saw Peter Cox both had a point to make, so I'm going to invite them to unmute and say what they have to say. That might kick things off a bit. So Peter, would you like to go first, and then David?
Yeah, sorry, Colin, took a while to unmute. Yeah, I think seems like a reasonable plan. The issue about the historical record, though, is it's very much associated with the very high climate sensitivity, as you hinted. And I think it would be a mistake to try to modify the forcing just on the basis of that without dealing with the basic problem, which is high climate sensitivity. And that seems to be, although we don't know for sure, related to cloud effects. So the issue will be either at this one or UKESM-2 is how you entrain people working on those parts of the model, because at the moment they seem to be outside of the project team. Maybe that's true, maybe it isn't. But it feels like if you have this break between system components and radiative forcing, essentially, and climate sensitivity can and seems to be falling through the cracks. So I wonder whether you've got any comments on how that's dealt with.
Yeah, so I agree with you. And when I say somewhere, I think I say there the Earth's response, the Earth system response, I include the cloud response in that Earth system response. So we need to get into that space. I think you're right that in the context of UKESM-1 and GC 3.1, we didn't have enough interaction. We essentially took what we were given, and we need now to be more solidly involved in, let's say, the development of the physical model GC5. So as I think I mentioned at the outset, within the context of GC5 development, the Met Office will have something they call the historical PEG, Process Evaluation Group. And so the Met Office have now, let's say, accepted the argument that we pushed very hard back in 2015, and I think failed to get through, that we need to concentrate on getting a good historical simulation, ideally for the right reasons, but we need to get a good historical simulation. And part of that, as you say, is understanding the feedbacks that drive the response in the historical, but ultimately drive the response in the future as well. So I agree with you, and we need to, as tightly as we can, make sure that this theme 2 that we're working on collaborates with that historical PEG as a start. Okay, David, do you want to say what you had to say?
Hello.
Hi, go for it.
Okay, I mean, I think I had similar points to Peter, perhaps, and I think things that you've said already. But I would, I don't know if other people listening who are perhaps more associated with IPCC could comment, or policy in general. But I'm assuming that the high climate sensitivity, both in UKESM and in other models contributing in CMIP6, is going to be quite a hot topic at, for IPCC and you know, in the future. So I think anything to understand if those high values are correct, or if we can understand why they are there, is obviously going to be very important. I think that's all I wanted to say, really. Okay, so it already is a hot topic, and there are people on this call who are more involved in dealing with that hot topic than I am. So I think there already is a fair amount of work in the wider international community looking at the plausibility of higher TCR and ECS values. And whilst I would say that work is saying they are highly unlikely, I don't think it's possible to rule out completely. Other people might want to comment on this, an ECS of around about 5, but they are highly unlikely. So that makes our model what I might say is a high impact, low probability future. So it doesn't discount it, but it makes it unlikely.
and other people. So I don't disagree with you at all, and I think we should be spending some time on both understanding why we get that, but as you say, understanding the plausibility of it. But I'm not sure it's an easy thing to again, it gets back to saying, can we say something about the past, and does that translate into future? Go ahead, Peter.
Yeah, so I mean, I think the difference is this time, Colin, is that two things have happened at once. Is that models, and certainly not just the UK model, have drifted towards higher ECS values, but also the observational record is giving more evidence of feasible ECS values, and they're going in opposite directions. So there is as you say, there is a huge crunch point here, and the IPCC clearly in its second order draft is trying to tiptoe between this, but it's very difficult. The difficulty we have now that is different from previously is that the ECS range that the CMIP6 models have, particularly at the high end, doesn't look to be consistent with the observational record, because basically all models have very high ECS and TCR specifically do not look like the warming over the last 50 years. It's not just UKESM. It's all of those models that got very high TCR values, and that is correlated with ECS as well, do not look like the warming in the recent past, and not that recent, the last 50 years. So there is a genuine, it isn't like before where we said we can't rule these things out. You can't ever rule anything out completely, but they look unlikely given the global warming record we've seen, very unlikely.
Yeah, I agree. I wouldn't disagree at all. I think that particularly the sort of, I mean, I split things into post-1990, but you say even longer, but I think post-1990, our own model, as you say, it clearly is not reproducing the real world trends. It's interesting to dig into why that is. So cloud feedback could be one. I was interested in the Arctic work. Arctic, of course, could be another, that there's things in the Arctic that are amplifying the global response. Yevgeny, do you want to? Yevgeny, you have a comment? Do you want to comment on that? What you've written there?
Yes, thanks, Colin. It's some kind of probably a bit of a parochial question, I'm not sure, but I'm coming from the. Can you hear me?
Yes.
Okay. I'm coming from some kind of a bit of a process modeling approach. I'm just wondering whether we can shortlist some first order key, basically caveats in the coupled system between the atmosphere, ice, and ocean. Mostly, I'm sort of having in mind the high latitudes, where we can see our models underperforming and might be a reason for some biases. It sort of taps into the activities outside UKESM clearly. It's quite often to do with the model development and specifically development of the model physics around sea ice and ocean, but maybe just consider this, what we can do in this direction.
Yeah, okay, agreed. I think there are some discussions around that in the planning of this 1-year extension. So just coming back to what we've got proposed, so I think Peter makes a fair point that we should be concentrating, at least for the latter warming period, more on the climate response than the radiative forcing. The earlier period, the cold problem we have is in the mid-century, maybe more a radiative forcing one, but yeah, it's the combination of the forcing and the response, without a doubt. Yeah. So we should take that on board. Do any people have any other comments on these three themes that we've got, and whether what people feel we're doing something crucially important, or not fitting with their primary interests, or something that we should be modifying in any way? Trying to look at the chat and just see if there's any hands. There's things coming in here instead. Graham says the climate response to volcanic forcing. Yeah, I don't disagree. We've got a bit of work going on in that direction at the moment. If you want to elaborate on that, feel free to unmute, Graham.
Yeah. Yeah, I mean, it'll be interesting to analyse the UKESM volmit runs. The question of the high climate sensitivity. You know, obviously in the volcanic case, it's mainly a shortwave dimming effect. So I don't know how sensitive UKESM is in those volcanic periods in relation to these changes in ocean heat content as well, particularly through the 1960s into the 70s. Then I think some, you know, having this pre-industrial baseline experiment to exactly test the volcano climate sensitivity and compare that to the other models. We'll obviously get some information there, but it's, you know, from Leeds' perspective, we are less the experts on climate response, and if we could work with somebody within the UKESM team to specifically to analyze those runs and get a heads up, you know, about how that's looking. I don't know about that, if that's within scope of. I mean, we have this proposal in at the moment to look at the 1960s and the Agung, the response to the Agung forcing in relation to the changes in the North Atlantic multidecadal, in the Atlantic multidecadal oscillation or variation, and so this interplay between the ocean heat content changes and the forced variability, whether it be CO2 or a volcanic solar dimming driven change, then, you know, I think these are the things we need to try and piece together between the MIPS to understand how much is tropospheric aerosol change, how much is volcanic aerosol change or sensitivity to those changes. So yeah, I think including the volcanic aerosol forcing within that any analysis is, you know, these are obviously big forcings in the historical record, and it's something that will help shed light on this.
Yeah. Okay. So I agree. That's something that we could try and put into that theme too. Yes. So agreed, and it's something that would be useful, I think. Yeah. I'm getting a note that Bill Collins has his hand up, and then there were a few comments, and then I've got one thing to say as well about climate sensitivity. But Bill, you have your hand up, so I'm going to go to you because you've been.
Yeah, well, sort of related to climate sensitivity and climate feedbacks, particularly in theme 1, is that current definition of climate sensitivity is all based on this pre-industrial plus 4 times or 2 times CO2 step, which obviously isn't an applicable baseline for looking into what's going to happen next. And the other point I wanted to make about the feedbacks is that this is something that really needs broken down sort of process by process. I mean, I think it's brilliant how many, and I totally agree with what you said about how many sort of prognostic physical processes there are in UKESM-1. I mean, I think it's definitely, you know, leading the world in this, but it does mean that there needs to be some really quite well thought out quantification process to break all this down. And as I said, pretty much the 4 times CO2 that is typically used is perhaps not the best place to start from this.
Yes, I agree, Bill. And I mean, I think it was you that developed the kind of feedback framework for this that Alistair was then taking on board to try and break things down. But of course, we lost Alistair to GMED. So I agree with you, and we do need to be able to sort of break apart all these feedbacks and try and understand them, and try where we can to quantify the ones that are reliable and the ones that are not. Agreed. Just a quick comment to Rowan about changing the order of themes 1 and 2. We did have them the other way around to begin with. We flipped them around because we thought this would be a better selling point to NERC, but I appreciate your scientific view that theme 1 comes before theme 2. It does in my mind too, but we thought it would sell better to NERC with theme 1 at the beginning, but we can always flip them back. There was a comment. Yeah, go ahead.
Why did you think that? I don't agree.
Because NERC has such an emphasis on what you refer to as the solution space, and therefore the solution space is all about the future, we felt.
But But if it's not consistent with the past, then we have no confidence in it. So theme 2 is fundamental.
I don't disagree with you. Yeah. So if there's a strong feeling for people that we should flip the order again, then we had the order as you just suggested. Theme 2 was theme 1 and theme 1 was theme 2. We flicked them around a little bit, both for NERC selling point and also because the number of institutes interested, there was more apparent effort wanting to go into theme 1 than theme 2. But I completely agree with you from a sort of scientific perspective. So we'll come back to that maybe in the discussion tomorrow and see what people think about flipping them back again. I saw there was a comment from Paul Holland about, do we know anything about the spatial patterns of where we're going wrong in the response, the climate response? Paul, do you want to enunciate on that? And then I don't know whether anyone can comment or whether it's possible to comment.
I think it was answered in the chat. So the warming is all in the deep North Atlantic apparently, which means it's not my problem, so that's great. My question was whether the Southern Hemisphere and the general, there's an absence of polar amplification in the Southern Hemisphere in the OBS, and typically that's not the case in the models. So I was wondering if that was a problem here, but apparently that's not the case.
Okay. I wouldn't be as confident as what you've heard in the chat that we don't have a problem in the Southern Ocean, personally. The one thing I was going to say, and I'm a little bit risky in saying this, so the FAST model that we've developed, one of the things in particular is it has a coarser vertical resolution. And we have made one 4x CO2 experiment with that, and it's very early days with it. But it has an ECS of 3.8 degrees, not 5.3. And it does clearly have a different cloud shortwave feedback response. And it's the first time we've seen that. When we had an N48L85, we didn't get a change in the cloud feedback. So I'm just indicating there that we might, by chance, have stumbled on a way to at least begin to try and understand where we might be having cloud feedback things that are driving a higher response. It will be interesting when we get that model in a state to be able to run it through the historical period, what it looks like. And I don't discount the fact that having higher vertical resolution may be giving us problems in inverted commas in simulating cloud feedbacks. So I view the lower vertical resolution model as possibly a way of understanding what's happening in a higher resolution one. I want to stress it's early days with that, but we think there's just possibly something to get our teeth into in the context of theme 2 there with one of our own tools. Okay, I'm trying to see, is there a working group looking at the causes of high ECS? I think, to be fair, I would say there isn't. There is a group now that will, part of the Met Office development of the physical model, they will now run what they call AMIT plus 4K experiments. So they will at least know what the cloud feedbacks are like and what the different feedbacks look like in a new model before that model is put into a coupled state. So there will be some more tracking, let's say, of the response in these ECS-like frameworks going forwards. And again, we should engage with that as much as we can, I think. I'm trying to look if there's anything more that people are pushing. I don't see any. Yeah, Julie had a point about reduced complexity, and it's a point that I'm quite keen on as well. Do you want to unmute and just say what you think in the context of reduced complexity?
Yeah, sure. But can you hear me like this?
Yep, certainly can.
Great. This is the primary impression I have had from all these talks, and I was really impressed with the quality, is how UKESM General has reached an astonishing level of complexity. And it's really impressive how much you have made progress since last year, but also how we are now capable, as a community, or myself, of representing all that complexity in all different processes and their relationships. Now, that complexity is a bonus, of course, but it also creates a witness for our community because it makes the analysis, the interpretation, the quantification of uncertainties even more challenging. And it seems to me, even though I'm not an expert, but it seems to me that the ECS and PCR problem precisely there's a challenge to reduce it because it could be related to that complexity. And my feel is to actually come back to reduced complexity configurations. So I'm not saying developing a new model, but somehow there were some tricks about this in the hybrid modeling presentation we had earlier today, that then we could see if the structural problems, or at least the problems that we have identified with UKESM-1 still remain, or if they are somehow alleviated. And I would include in those reduced complexity approaches with assimilation of the observations, or plain, I think that was something introduced in the fire presentation, where you use observations instead of parts of the model and see how the model reacts to that. And my feel is that maybe that's a strategy that could highlight efficiency onto which parts of the processes or which part of the extra complexity that was introduced is responsible or not for those remaining failures or weaknesses.
Yeah, okay. I completely agree with you that we need to be able to run the model in slightly what you call reduced complexity. In respect to the TCR and ECS, so our reduced complexity model, of course, is the HADGEM3 physical model in some ways, which is the core of the Earth system model. And without wanting to sort of pass the buck, the physical model is where the high TCR and ECS has its source, and it is primarily in the cloud feedback response. And of course, the conundrum is that some of those new cloud feedbacks evaluate as being better. So it seems to be indicating that there are other cloud feedbacks, potentially in the tropical region particularly, that were being masked in their contribution to climate sensitivity in earlier models that are now not being masked. So I think this waylay into high climate sensitivity is actually possibly progress, but it's a long route to progress, because there is the potential for us to be maybe getting the right sensitivities for the underlying right reasons ultimately. Previously, we may have been getting them for the wrong reasons. So to some extent, our reduced complexity model is the physical model, but then we can do these other things with vertical and horizontal resolution to see if there's a sensitivity there as well. The other thing with reduced complexity, it allows us to explore parameter space more quickly. So our model is heavy to run computationally. Does anyone have any comments on this theme 3? So one of the things we thought was important is that we started to broaden our community a little bit and actually interact with the policy community and the impact research community. And that the idea was to try and have a workshop, a community workshop with each of them, which these would deliberately be forward-looking, and that we would highlight the things we can do with our models and the simulations and data we can provide to them, but we would also be asking them what they saw as important from an Earth system model going forwards, and that might help us with a second project in some ways to sharpen a second project from their perspective. So in the last few minutes, does anyone have any comments along that line, this theme 3? So we thought 2 community workshops. Yeah, to answer Lee, the intention is that we will have something either in the run-up to COP as well as at COP. We think it might be better to have something in the run-up to COP actually, as much as we could. So if there's anyone that have, so of course COP has been moved to November 2021, so it's right in the middle of our 1-year extension. So it would be nice that we certainly had a policy-oriented workshops well before COPs, and we can have some discussion with them, and that might help us sharpen a presentation for COP itself. The other challenge that I've found we're having is to identify and get good collaboration with the impact community in the UK. It might be my ignorance, but I have better connections with the impact community in the rest of Europe than in the UK. So some help in that direction would be helpful. Has anyone else got anything they want to bring up? If not, I am going to go to the last slide and then I'm going to stop. Theme 3 was there. That was where the user outreach program is going to go, I think. The feature of the model. That's correct, Jeremy. Yeah. So as well as these 2 community workshops, we will also keep working on what we call dissemination to the wider public and science community, so they know about what we're doing in language that hopefully they can connect with. Right, I'm going to spend the last 5 minutes and I'm going to finish on time. So I'm going to go very quickly here. I mentioned this already, that there's a potential LTSM2, and I stress potential only, and we've proposed these 4 themes as something that might be what we can collect an LTSM2 on sort of science for global change mitigation around, and you heard talks on these 4 before. And the implication of those 4 is that we are looking to have a model that covers these kind of things, which are written here. And to some extent, we see this as, looks like there's a lot of things there, but a number of them are evolution from what we already have. So Antarctic ice sheets, methane emission-driven fires are things that are moving and are in process. So just on a very last point, does anyone have any sort of headline things that you think we should be, addressing that we're not in these 4 tasks: carbon budgets, mitigation strategies, near-term climate forces, abrupt change, and the model that we think we might be having to address those questions? So please throw something into the chat, and we are going to close in a few minutes. It's a crucial pint. Pint is what we would like, Yevgeny, but I guess you mean point. Okay, it's deadly silence, so that either means I've disconnected or everyone else is disconnected. Okay, here's one. Human land use is great. What about man-induced processes like agriculture, irrigation linked to barrage reservoir? There's a lot that came now. Not convinced. So human land use, we are trying to address. If Chris or Andy Wiltshire are online, they can answer these questions better than me. I think the human response, meaning the response of humans to changes and then the change in human response changing the scenario, is a step too far for us. Things like irrigation we are interested in. Peter's comment, not convinced tipping points can be addressed with an ESM. Fair point. Is that either because of the cost or their ability to run, or the fact you need a massive ensemble to address these things?
Yes, all actually. So I think the thing is that you're talking about a small part of parameter space by definition. So in order to know the risk, you have to do many ensemble members. But also there isn't much evidence of tipping points in the current Earth system models. So I think you might argue that that's going to be a slightly forlorn exercise to do that with ESMs. It's not to say it's not worth studying. It's just it's not necessarily an ESM activity at the moment.
Right, and the fact that ESMs, so I don't know that I don't know enough about the subject to necessarily agree or disagree with you, that they don't show abrupt risk of abrupt changes and things. Is that a good thing, or is that they are too safe, as it were, in inverted commas?
I think that's open to question either way. I mean, some people say they are too safe, but if you look at the things like the TCRE, the relation between global warming integrated emissions, it's unbelievably linear in models into the future, even ones with very high climate sensitivity. So there isn't, you have to search really hard in these models to find the sort of tipping points that we worry about in simpler models, and so therefore you're going to have really large ensemble numbers, I think. So I just feel that that's possibly the wrong use of ESMs. Right. Okay.
It would be good to talk more about that, because the people in the various NERC centres are very keen on having that as a topic. So I agree with you. There's a conundrum to cross there. If you need the processes and you need the ensemble, then it's hard to get both.
Can I just add there's maybe scope?
Yeah, sorry, go ahead, Rob.
It's coming on to Peter's point. So is there scope for stuff like machine learning based emulation of a more complex ESM to sort of increase the parameter space we're looking at? So we're already starting to do that kind of thing with components of the system model, but I don't know how much the scope there is into kind of expanding it up onto the full Earth system model. But basically using the ESM to generate and train a more simplified machine learning based emulator type thing.
Yeah,
then you have a giant parameter space to then explore.
Yeah. So I think in that case you might emulate individual components, which might actually be more complex than the ones you could afford in an ESM, and you might see nonlinearities. Of course, if you're trying to emulate the entire ESM, it has to have non-linearities or tipping points evident in it for you to emulate them. So I think it would have to be something that's building up, as you said, Rob, individual emulators for different components. I think that is possible, but it's not really an ESM approach. It's not to say you can't do it.
Yeah, cool. I get your point. Yeah.
Yeah.
I think we are quite keen from like the NERC side to have some machine learning AI underpinning stuff in some of these activities as well. That's why I was coming from, kind of the emulator aspect there.
Right, I think that's useful to follow up on, and Ken's just written that there is a meeting that was going to be in Leeds in January that is somewhat in that space on uncertainty quantification. There's a couple of comments about downscaling, and I agree with you. There is an activity that's called UK Environmental Prediction, which is really about regional environmental prediction, and there has been some discussions about how to move that into some kind of downscaling of an Earth system model. That would not be our project, that would be something else that we might have to interact with. But I agree that that's something important for us, not necessarily in our project, but to try and emphasize that that is an important thing to be able to connect with more, let's say, the user space as well. I saw there was a question about N216 Orca quarter. I think the answer is probably, as the standard model, no, Pat, simply because of cost and because the Orca quarter at the moment is not performing sufficiently well scientifically. But we would like to have an exploratory model that we can do things at that resolution. So maybe not the workhorse, but an exploratory model. As we're running out of time, I'm going to suggest we try and pick up the other things into a Google Doc, and that will allow us that are developing these to think about things a bit more and maybe respond to what you said there, both in the context of the LTSM2 and the 1-year extension. So hopefully we can collect all those up. Okay, I'm going to wrap up now. Those of you that are on the advisory board, you're lucky enough to meet again in 1/4 of an hour. We won't try and keep you for long, but we would like to tap your advice just quickly. And there's a new Zoom link for that if you haven't received it, Hazel, I'm sure we'll send it to you again. So in closing, this is the first and I hope the last online General Assembly. We don't know that for sure, but let's hope it's the last one. So I do want to thank all the speakers. I thought the presentations were really good and people kept on time. I want to thank the audience because there were questions all the time. That was really good. I want to thank a number of the people in the UKESM core group who agreed to be question moderators and organize things and this kind of stuff. We had a little organizing committee that was myself, Rob, Jeremy, and Hazel. I think it was only the 4 of us in the end. So thanks to the organizing committee. Thanks to Francesca from CEDA who came and helped us on day 2 to organize getting people in and out and this kind of stuff, because the technical side of that is not straightforward. And without doubt, the biggest thank has to go to Hazel, who has organized everything to do with the practicalities of getting the talks together, making sure that they're all joined up in presentations, that people keep to time, and giving us instructions about how to keep people to time and what to do with Zoom. And